Hello everyone. So good evening. Welcome to the second session of this Aspen course. So yeah, I have gone through the queries in the NPTEL website and found that most of the questions are related to installation and license errors. Right? Anything else except this? Few couple of technical questions were asked. I have responded for some of them, and I will be discussing few more things in this class. All right. So yeah, before that, am I audible clearly? Any response?
Yes.
Okay, that's great. Okay. See, regarding this installation and license issues, I have contacted the coordinator. Okay, so I'm yet to get a proper response from the coordinator. All right. So as of now, no, we have to put it in a pause, the installation procedure. Okay, because I have been given the responsibility of tutoring and discussing the technical issues and not the installation aspects. However, I have communicated whatever issues you have been posting online to the coordinator. Okay, so we are yet to get a response from them. Okay. Yes, yes, I have gone through this assignment to question 6 to 10. The question itself is missing from the assignment sheet. Yes, I have asked for this one as well. I'll respond once I have a reply. Okay. So anything else except these two, installation and assignment one? You can just put it on the chat box. Installation, license, and assignment 2. Except these, any other issues you have? Okay, so we'll do one thing. I'll just revise whatever professor has been discussing this week, and then we'll solve some few problems. Okay, just basic fundamental problems. At least for till fourth or fifth week, we'll just see and get used to the interface of Aspen. After that, we're gonna solve some industrial related problems. Okay, direct flow sheet simulation, some optimization of design variables, etc., etc. So for the people who have come first time, so I'm Chaitanya. I'm a PhD student from Department of Chemical Engineering, IIT Madras. Okay, so yeah. See, in case of assignment submissions, it will be extended, all right. So don't worry about the deadline. If question itself is not given in assignment, we can't expect people to submit it. Okay, so don't bother about the last date for it. Okay. So yeah, we'll start with the summary of the weekly lectures, whatever happened this week, and then go through a couple of questions. And if you have any questions related to this week lectures, we'll discuss over it. Okay. So yeah, so this week professor started with the individual component. So he actually explained what individual component means and how to simulate these in Aspen and etc. So he started with mixture, splitter, took one of the example mentioned over here. But no, explaining those the explaining the same thing would be it's a repetitive, right? More than that, I would like to just ask a simple question. So in case if we have a mixture, let's say in this example only, so on the left hand side of the slide you can see a mixture, right? So now I have a fluid with mass flow rate of m coming from top, and fluid with mass flow rate of twice of m dot. Okay, so it's m and m, 2 m dot. Okay, so the above one is coming at a pressure of, let's say, 10 bar, and below one is coming at a pressure of, let's say, 5 bar. Now I want you to tell me what would be my outlet pressure. Can anyone tell? I'll just repeat the question. From top, I have a fluid which has a flow rate of m dot, which has a pressure of 10 bar. Okay, and from bottom, I have a fluid which has flow rate of twice of m dot and with pressure of 5 bar. Now I want you to tell me what would be my outlet pressure. Any response? So I have 10 bar from the top, 5 bar from the bottom, whereas the mass flow rates are exactly opposite. Okay, m dot from the top and twice of m dot from the bottom. So what will be my resultant pressure? 15 bar, 15 bar. Okay, any other response? 5 bar. Others got the question right. In case if you didn't understand question, please let me know. It's just a simple exercise. 15 bar, 5 bar. Okay, thanks for your responses. Any other answer? I'll just wait for a minute. Okay, let others think over it and give a response. Okay, so most of the answers are 15 bar and 5 bar. Okay, now just let me ask you something. When you mix two fluids at different temperature, you will have an equilibrium temperature, right? So now come to this example. Now you have fluid A coming at 10 bar in this direction, you have fluid B coming at 5 bar in this direction. So where would be my resultant direction was? For example, let's say in force itself, if you are trying to calculate net force, you have 10 Newton in this direction and 5 Newton in this direction. Which direction my net resultant would be? In this direction, right? It will be the way. So in this example, if you are mixing a fluid at 10 bar and 5 bar and expecting fluid to come out of the tube in the third direction, it won't happen. You'll have a backflow. Okay, so it essentially says that you should never mix two fluids at different pressures. It won't happen. Okay, so you'll always have backflow. So the question itself is asked to confuse people. Okay, so idea is you can never mix fluids at different pressures. You'll have backflow in the system. So all 15 bar, 5 bar, or all, no, you tried answering, that's an appreciable thing, but you should have also thought now what is exactly happening over here. Fluids at two different temperatures can be mixed, whereas fluids at two different pressures can never be mixed. So now let's extend this to the splitter case. Let's say if my fluid is coming at 15 bar. Okay, now I want fluid which is coming from the top and fluid which is coming from the bottom at different pressures. Is there anything which I can do in a splitter? So my inlet pressure is 15 bar. I want to split it as say 5 bar and 10 bar. Can I do anything in a splitter option? Is it possible to achieve that? See, physical is just a physical splitting. Okay, for example, if I have one bucket of water, I want to put it in two buckets. It's just a physical split, right? In the example which I'm considering, it's just a batch process kind of thing, right? Here it's a continuous process where it's just physically getting split. So if I have a fluid at 10 bar, I want to split it into two, my two outlets will be at 10 bar. All right, however my mass flow rate will be different. It's obvious, right? Conservation of mass. Okay, so my outlet pressures will always be same in splitter. Okay, so don't get confused with mixtures and splitters. In mixtures you can never mix two fluids at different pressures, whereas in splitters you'll always get same fluid when you are same pressure at the outlets for whatever stream you are splitting. All right, so is this clear? And yeah, I just talked about the batch process, right? There was a query in the online thing, one asking the statement says, is steady state process same as continuous process and dynamic process same as batch process? No, see, these are different classifications. Okay, steady state and dynamic is one set of classification, and continuous and batch process is another set of classification. So if I want to go into detail, for example, in steady state process we consider each variable is invariant with respect to time. Okay, so if we are talking something change with respect to time, and if we find that there is no change with respect to time, then we call it as steady state. Okay, this is different from equilibrium is a different concept. Don't get confused with equilibrium and steady state and dynamic process. All three have got different definitions. Okay, now dynamic means if something is changing with respect to time, that comes under dynamic. Okay, now in continuous and batch process, so continuous, for example, if you see the mixture aspect, whatever we talked about of the splitter, it's continuous, right? You have inlet and outlets. Whereas in batch process, for a fixed time period, you'll have some kind of reactions will be taken. Okay, okay. So these two are different sets of classifications. For example, while solving your continuous set of problems, if we assume equilibrium exists, we minimize Gibbs free energy. Whereas in case of batch process, it can be one of example, could be reactor. Okay, we minimize Helmholtz energy. So it's different approach for continuous and batch reaction systems. So we'll go in details when we talk about thermodynamics of reactors and all, right? And yeah, the next example which professor discussed is about flash. So yeah, we can discuss one more example over here. Okay, so for example, if I in the case where professor explained the flash calculations, he took example of naphtha, toluene and water, right? So we'll just simplify it. Okay, so if I have a binary system, let's say mixture of nitrogen and oxygen, it's a simple example, right? Air, let for no neglect argon. So if I take nitrogen and oxygen 50-50% feed, and I'm sending it to a flash split, flash splitter at let's say 100 Kelvin and 10 bar. So what composition would you expect to be in vapor phase and liquid phase? Will it be the same composition as the feed, or will they, let's talk with respect to nitrogen. In the feed I'm saying nitrogen is 50%. Now what is the composition of nitrogen in vapor? Will it be more than 50% or less than 50% or equal to 50%? I'm doing a flash calculation at 100 Kelvin and 10 bar. Okay, 100 Kelvin and 10 bar. I took it as an example. All right. So any response? Could you get the question? First asking before asking the answer. All of you, could you understand the question, or shall I repeat it? Yes, okay. See, I have a feed which has mixture of nitrogen and oxygen. All right. My feed composition is 50% nitrogen and 50% oxygen. Now I'm saying this feed is at 100 Kelvin and 10 bar. Okay, 100 Kelvin and 10 bar. Now I'm sending it to a flash column. Now I'm asking, and I'm separating it to vapor and liquid phases. All right. Now I want to know the composition of nitrogen in vapor phase. Will it be higher than the feed or lesser than the feed or equal to feed? Is this clear now, the question? Now we are discussing the flash calculation, not the splitter nor mixture. Okay. Any response? So the people whoever okay, the vapor phase is which pressure? Okay, we are neglecting the pressure drop in flash column. Okay, for example, the feed is at 10 bar. I want vapor is also at 10 bar. Okay, or let's say we are expanding it and then separating it. Okay, vapor is at 1 bar and my feed is at 10 bar. So one response says depends on K values of O2 and N2. Yes, that's a good response. Less than 50%. Okay. So could you please explain how you are guessing that it's less than 50%, Mr. Akshay? Or the people who told it's higher also, just out of curiosity, just asking how could you just tell straight away? Because one of your friends says depends on K values of O2 and N2. So irrespective of the K value, how could you just say that? So another person says depends on how much pressure we want. Okay, so if you're talking about pressure, it's indirect way of mentioning the equilibrium constant. Okay, so both are related, so it's indirectly the same response. Okay, bubble point of nitrogen. Okay, see, when you're talking about pure fluid, okay, you call it as boiling point. There's no bubble point and dew point for a pure fluid. When you're talking about a mixture, you get a bubble point and dew point. Okay, so if you're trying to point out nitrogen, you can say boiling point, not the bubble point. So I'm calling it as boiling point of nitrogen is greater than oxygen. Okay, so if my boiling point of nitrogen is greater than oxygen, 77 Kelvin, and no, it's the other way around, right? Nitrogen has a boiling point of 77 Kelvin and oxygen has somewhere about 83 Kelvin. So oxygen has a higher one. Depends on volatility. Yes, it's a response, correct, proper response. VLE curve. Okay. See, all the answers whatever you are giving are quite relevant. Okay, so it depends on equilibrium constant, it depends on the pressure at which we are talking, it depends on boiling points of individual components, it depends on VLE curve. Yes, all answers are relevant and all are related to your flash calculations, which is having same chemical potential in vapor phase and liquid phase. We usually don't solve problems with respect to chemical potential, we solve using fugacity, right? So we equate fugacity of individual components in vapor phase and liquid phase. Okay, so generally when we expand it from 10 bar to 1 bar, what the question which we consider. So when we are expanding it from 10 bar to 1 bar at 100 Kelvin, so the temperature also comes down, right? Expansion causes expansion reduces the temperature depending on wherever we are location relevant to our inversion temperature. Okay, so we'll be below inversion temperature in this case, all right. Okay, since we are expanding below inversion temperature, there will always be a reduction in temperature. In case if you are expanding higher than the inversion temperature, you will have a rise in temperature with drop of pressure. So in this case, for sure we will have drop of temperature. So from 100 Kelvin we will have drop about approximation. Okay, I have done few calculations in the past, so out of experience I'm telling the value will be somewhere close to 80 Kelvin. So at 80 Kelvin, the vapor fraction, the nitrogen fraction in the vapor phase will be more than that of oxygen. Okay, so if the feed mole fraction is about 50% of nitrogen and 50% of oxygen, our vapor in vapor, the composition of nitrogen will be higher than 50%. All right. So you just try to distinguish between mixture, splitter, and flash. All three look to be same. However, in a splitter, it's just a physical split. There is no change in composition. However, when you're doing a flash calculations, flash separator, flash column, your composition will completely be different. All right. So that point one need to understand very clearly. Now the second, the third one is the fourth one, right? So the fourth one which professor explained is decanter. So decanter basically used for separating this, excuse me, LLE split. If you have liquid split, then decanter is usually used, right? It's the same as the flash separator. In flash you have VLE, whereas in decanter you have LLE. It's the same thing. Thermodynamics remains same. Okay, and next he explained about heat exchanger, a simple heater cooler combination of both. And then he has come to a multi-stream heat exchanger. So these multi-stream heat exchangers are quite used in LNG process and all, right? So what is difference between a simple heat exchanger and M heat ex? So when you're talking about multi-stream heat exchanger, you have multiple cold and hot streams. Okay, so there's a possibility that it can accommodate n number of hot streams and n number of cold streams. When we progress in this course, we'll actually solve a lot of optimization problems and process design with respect to the multi-stream heat exchangers. Okay, so we'll discuss more about pinch analysis and in future. All right. Then he discussed about different types of distillation columns available in Aspen, which starting from basic approximate model to the exact, not exact, okay, a better version, a better prediction of results. So different kinds of distillation columns were explained in the slides. Then yes, absorption column, then extraction columns, all these things were explained. So yes, till here is everything clear, or do you have any questions to be discussed? Any questions?
No, sir.
No, right? That's great. Okay, so I have very few questions for you. Okay, towards the end also I'll in between I'll keep on asking anything need to be discussed, and also please respond. Okay, we'll add few more points. So this is the question for you. If there are two outlet streams for a mixture block, so whatever we discussed previously, we observed that for mixture we have only one outlet, right? So in this case, the second part is, which what is the second outlet in with respect to Aspen? So this question is very specific to our Aspen software. Okay, yes, if you know the answer, you can just put it in the chat box. Okay, I know that people are very much into this Aspen and they know all the answers, but let others also think. Give others the time. Okay, if you already know the answer, just put it in the chat box. Okay, let others think and answer. The people who didn't see in Aspen, I'll just see. Okay, this is one of the five. So yeah, I'll create some more. So we are talking about mixture, right? And I'll create a new all right. See, when you go to model palette, you'll have a mixture here. Okay, just put it up. So I already gave two inlets and one outlet. Do you see this? So we have the second one over here, right? This is what the question is. So if you just go over it, you will be able to see that water decant for free water thing. Okay, so this is what the question has been asked. All right. Yes, I think good number of students have answered. Thanks for your response. Yeah, this is the answer, right? Now specifications based on I'll just post this in this query. Okay, not query, polls. Okay, so this is one more question. So now we are discussing with respect to split. So in Aspen, what are the inputs that are required for completely specifying the split uh, block? For the people who have already used the Aspen, they will be able to answer, and who are unable to have, who don't have access or don't have access at this moment, just follow my screen. Okay. Please do respond on the poll so that I'll have a quantitative analysis. So out of 49 students, only 13 have answered. For others, this question seems very poor, is it? Yes, if you have any queries, you can just put it in the chat box. Okay, let's see this one. So I have a split. See, this is the one which we are talking about, splitting. Okay. So I gave one inlet and two outlets, right? So if you're going to split, you'll be able to see the split fraction. So what fraction of the inlet would you like to give to stream 16? Another one which you have is the flow. Okay. So you can also specify flow, you can also specify limit flow, multiple possible values. But essentially, one need to understand that for solving any block, the number of degrees of freedom is really important. So in case of splitter, just take a simple example. If I know that, let's say, if I will just take a simple example. If my inlet flow rate is 10 grams per second, okay, if I already specify that one of the stream flow rate is 2 gram per second, then the second stream flow rate will automatically get fixed, right? When I put a control volume here and put a mass balance, the second stream flow rate will automatically get fixed. So one need to understand the degree of freedom available with individual block or unit very clearly. Without understanding it, if you just keep on giving the input to the system and ask it to solve, it won't happen. It won't be able to solve. It can happen that it is under specified or over specified. Unless you give completely required inputs to make the degree of freedom available with the system 0, you won't be able to get a appropriate solution. Okay, so in this case, you have degree of freedom of only one, so you can specify only one. Okay, no more than that. So this question has multiple answers. Okay, so the people whoever have put B and D, no, seems I think you have already gone through it. And okay, fine. Okay, so yes, okay, So see, this is one of the flow sheet. Now we are filling data to the stream. Okay, so we have S3 stream, we fill temperature, pressure, and flow rate, compositions and all. Now I want you to answer what all the things which you can get when you go through the drop box A. If you have Aspen in front of you, can you just open it and check the composition part? What all things you can give? See, this is very simple one. Okay, this question is framed for you to just get used to things and get aware what all the things available in Aspen, what all things you can give. That's the reason this question is framed. Okay, it's very simple. If you have Aspen in front of you, can you just go through it and see what all the things available with you? Okay, I'll just finish this part and then come back to the question about this nitrogen and oxygen example. Okay. So people have opened it and have seen. Okay, you have license failed. Okay. As of now, I don't have proper response for the license thing. Okay, so I think people still have some confusion with the nitrogen and oxygen example. Okay, see, nitrogen has a boiling point of 77 Kelvin. All right. Now, if the room temperature, let's say I have a small block, and the entire block has nitrogen in it. Okay, it has boiling point of 77 Kelvin at 1 bar. The system is at 1 bar. All right. Now, if the temperature of the block is 80 Kelvin, will nitrogen be in liquid phase or vapor phase? Any response?
Gas phase.
It will be in vapor phase, right? So now, in the same case, the temperature is 80 Kelvin and oxygen, it has boiling point of 83 or 86 Kelvin. Okay, approximately, I don't remember exactly. Which phase oxygen will be in? And now we are talking about pure components. Okay, we are not discussing about the mixture. The pure
Sir,
component.
please repeat once again.
Okay, so I have a closed system which is at 1 bar, which is only of oxygen. Okay, given oxygen boiling point at 86 Kelvin, 1 bar. My system pressure is 80 bar. Which phase oxygen is expected to be in?
Vapor phase.
See, I'm going the temperature below its boiling point, right? Let's take example of water. Okay, now steam water has a boiling point of 100 degrees centigrade, right? If I am at 80 degrees centigrade, water no, it will be in liquid phase, right? If I am at 120 degrees centigrade, it will be in vapor phase. So for the temperatures above its boiling point, I will always be in vapor phase, whereas temperatures below the boiling point, I will be in liquid phase, right? Understood? Now, oxygen has a boiling point of 86 Kelvin. Now, if I am at 80 Kelvin, it will be in liquid phase, right? So, if I am talking of about 79 Kelvin after expansion at near 1 bar, So the concentration of oxygen in liquid phase will be more than the nitrogen, and in vapor phase it's the other way around. Concentration of nitrogen will be more than oxygen. So with 50% mole fraction at the feed, when I expand it to 1 bar, with a drop of temperature, my concentration of nitrogen in vapor phase will increase, whereas concentration of oxygen in liquid phase would increase. Okay, is that clear? It's not 80 bar, it's 80 Kelvin. Okay, good. Fine. So could you check this? What are the options available? See, there was again a query regarding the installation and the license one. See, license one, I have contacted the coordinator. Okay, I'm yet to get a proper response. Okay, so once I have response, we'll sit and do the needful thing for installation and the license thing. Okay, uh, the installation process and all is taken up by another person and not me. Okay, I have communicated whatever issues you have raised on the website to the person. However, I didn't get a response from. Still waiting for the response. Okay, so once I have it, then we can go further into the installation and the license related issues. Okay, I think this is very simple question. Let's skip this one as well. This is yes. So can you answer the question 7? The type of separator model used for separation of liquid phases. So before answering this question, what is this liquid split? Any response? Yes, regarding assignment 2, your question 6 to 10, there is no question. Okay, so I have communicated this as well. Don't worry about the last date of submission. It in this case, since you don't have question to respond, it will be postponed. All right. So what is liquid
I have to
split?
submit that from 1 to 5 only.
Okay. So where did you get this response from? Because I didn't get this response.
Sir, the last date of submission is tomorrow.
Correct.
So, for question 1 to 5, we have filled, but from 6 to 10,
Correct.
it
Correct.
seems it is.
There's no question.
So, hmm.
So how from where did you are telling that we need to submit only 1 to 5, no need of 6 to 10? You have any information from the coordinator? Because I didn't have any
No,
information.
sir. No, sir. Not
No,
like this.
no, right. Okay, see, in this case, since there is no question given over there, the assignment sheet will be updated and the last date of submission will be extended. All right. So as of now, you for the people whoever or who wants to submit it, they can submit it. But even for the people who have submitted it, it will be opened in future in case if the coordinator is able to change the assignment. All right. I have
Yes, sir.
communicated the issue with coordinator. Okay, it will be taken care. But don't take a decision individually. Okay. We are a class, right? We are a class of students, so better we take a collective decision. So yes, the seventh question, what is this liquid separation? Because I don't understand, I want to know, if I take a glass of water, do I expect to see two different liquids, do different separate liquids? Can anyone explain what is this liquid separation? One says it's based on density separation. No, you don't have to wait. You please submit for the first 5 questions. Since I didn't get response till now, I don't know the proper answer for that. Okay, so just I'll see, if I get a response till tomorrow morning, I'll put a mail for all of you. If not, uh, you please submit for 1 to 5 questions, okay? Because I'm not the one who have framed the assignment, it's another person. So we are three, not one. I'm the one who will be discussing your doubts, and one person works on the installation and license issues, and another person frames the assignments. Okay, so we are three. It's not, I'm not the only one who is into this course. Okay. See, I'm not asking you the answer for these two questions. I'm asking you, what is liquid-liquid split? Why does it happen? What is the reason for liquid-liquid split? Or can you give me just a practical example, a simple example, based on density difference, boiling point, oil and water, density difference. Okay, so with the knowledge, excuse me, with the knowledge you have, you are just telling it's based on density, right? You say, let's take an example of oil and water. That's the simplest example where you can see different liquid layers separation, but this is based on density. That's what you say. I would call it, this happens because of minimization of Gibbs free energy. There is something called a stability analysis of the phase. Okay, when you do a flash calculations, when you do flash calculation, you'll always check multiple feasibility of phases. Okay, so has anybody encountered this term called minimization of Gibbs free energy? Anyone from thermodynamics? Okay, no. Any other response? What is Gibbs free energy? What is minimization of Gibbs free energy? See, when you call a system is at stable and equilibrium, what happens is your Gibbs free energy of the system is minimized. Okay, so for the given system, if the if let's say we have two phase, okay, vapor liquid, I calculate Gibbs free energy to be some value G1. In another case, I consider three phases at same temperature and pressure, same conditions basically. Now in these phases, I consider vapor, liquid, liquid. Now for this particular condition, I calculate a Gibbs free energy called G2. Now I would compare G1 and G2 and see which between these two is a minimum value. For example, if my G2 is smaller than G1, I would say have a system with three phases, that is vapor, liquid, liquid, is more stable than vapor, liquid at that pressure and temperature, or at that conditions. Okay, so this stability of phase stability is calculated based on minimization of Gibbs free energy. Okay, so it's not according to density. Density, when you say we have phase split, liquid split based on density, it's very crude way of telling. What thermodynamically, if one want to say, it's based on minimization of Gibbs free energy, not based on density. Okay, just make sure when you go to an interview or somewhere where you have technical discussion, don't say about density, it's about the minimization of Gibbs free energy. All right. And yeah, in eighth question, I think some of you have already answered this, right? Okay. Okay, fine. Yes. So in the separator module, which is this question? Okay, I think this is straightforward. Just leave it. Okay, so here we have the 10th question. So we have two different distillation blocks. Okay, one is the when I call it as full form, you'll automatically have the answer. Okay, so you have two different distillation columns are useful for obtaining column parameters and provide accurate result. The statement, is it true or false? So professor explained about different distillation columns, right? So among all distillation columns, let me just post it on the poll. Yeah, the police one. So now I am claiming that DSTW or distill based on columns provide me column parameters as well as provide the accurate results. So is this statement true or false? If it is true, can you please comment about why you are calling it as true, or if it is false, can you please comment why it is false, or based on what knowledge you are telling it to be false? Can you just comment that as well? Any other responses? Okay, thanks for your response. Couple of you have responded. Okay, so one says it's based on some assumptions. What is that assumption? Some. You see, this sum is a very general term. Okay, if you are talking about sum, please elaborate. What is that sum? This happened with me, when I went to an interview. I just randomly told it does some calculation. So they pointed out me, what is that sum? You should tell clearly what is that sum. See, one says molar flow, one says molar overflow, equal volatility. Okay, there are multiple answers. We'll do one thing. We'll keep this question. I want you to read and come back for the next class, because I'm getting multiple answers. If I keep on telling everything, then you don't get to learn. You just keep on hearing. I want you people to answer this. What is the difference between a rigorous model and the one which has which is called as approximate model in Aspen? What is the big difference? Okay, I think 11th question would answer a part of that question. So just post a poll for 11th one. Okay, so the model that uses excuse me, Underwood method is what? One of the model in Aspen distillation simulation uses Underwood method. All right. So which among these uses the Underwood one? Okay, fine. So yes, as I discussed, there are two different kinds of models in Aspen. One is approximate model for distillation, and another one is accurate model for distillation. When we actually solve up at, we'll take up a crude oil distillation example in future. Okay, so this problem is actually the data which we are going to simulate is actually from a refinery. All right, so in future we'll be doing it. There will be clearly differentiating these two and discussing more in detail. That time, what I'll be expecting from you people, I want you to do a simulation and give me results. Okay, so by then all of you should have Aspen with you. Okay, so that's how our further sessions are going to be held. Okay, so I'll be giving you a problem statement and wanting you to respond. I'll be giving the steps to do while simulating or optimizing whatever question according to problem statement. Okay, I'll be wanting you to give response step after step. Okay, so we'll discuss more about distillation columns in future classes. Okay, and yes, and I want you to answer the difference between the simple approximate model and the rigorous model available in Aspen. No, you need not have to respond at this moment. You just go read about it and come back. Don't blindly come back, okay? Because I could see there is a wide range of answers over here. One says molar, one says molar. No, there is difference between molar and molar, right? So equal volatility. No, this is just wide domain. There's hardly any connection between these two. Till now, whatever answers I could see, I could see some thermodynamic connection, but this is really, it's like an open domain. The responses whatever I got now. So I want you to think over it, read over it, and come back. Then we'll discuss this in next class. Okay. Yes. So there's one more question. The type of distillation which we can't perform in red frac model in Aspen. So which among these is which among these can't be performed in Aspen? So I'll just raise a poll for this as well. Give me a second. So yes, can you please respond? The type of distillation which you can't perform using rat frac. And also give me a reason. For example, if someone says you can't model azeotropic distillation in rat frac, also just comment why can't you do it. That will be useful, right? Because it's just putting tick mark for one of the option doesn't make any sense. You should know why you are doing it. So in these classes we will be explaining more, answering more about why question, not about what. So I want you to answer why. For example, if someone says extracted distillation can't be performed, so why can't it be performed? What is the reason? If we do something, can it be performed? So all these questions should be answered, right? So one says multi-component distillation cannot be performed in red frac. Can you please respond why it can't be performed? So some people have responded regarding azeotropic distillation in coal, and some of you have answered says extractive distillation cannot be performed. So in all these three cases, can you please also comment? Why do you think it can't be performed in Aspen? Any responses? Okay. Okay. Due to solution temperature. What is the solution temperature? Take me as a layman person and can you please explain what is the solution temperature? Okay, let me tell you answer for this. See, the rate frac model available in Aspen does only the binary separation. Okay, so not only rate frac, any distillation column, when you talk about sequencing, which comes in chemical technology course or chemical process intensification course in anything, just a second. When you have let's say feed of A, B, C, all you can do in a distillation column is separate A from the top and BC from the bottom. Okay, so from one column you can get only one pure component. Okay, so if you have multi components, you'll get only one pure component in one column. So if for example if I have three component mixture, I at least need two columns for getting pure components of A, B, C separately. Okay, so a rate frac won't be able to do a multi-component separation in one shot, whereas when you have a sequence of rate frac columns, it will be able to do multi-component separation. Here, since the question is asked with respect to one column, it won't be able to perform multi-component separation. Okay, yes. Any questions you have, you want me to discuss today? Anyone, any questions? Yes, regarding software, I still don't have a proper answer for that. Okay, I have requested the coordinator for that. I'm yet to. Okay, you want me to explain about inversion temperature? Okay, I'll explain. Any other questions? The schedule is actually fixed long back. Okay. Uh, okay, let me come one after another. So see, uh, see, there is something called Joule-Thomson coefficient. Okay, so this Joule-Thomson coefficient says it's proportional to dou T by dou P. Okay. So it's essentially says that proportional to, not exactly. So a change in temperature with respect to change in pressure. At inversion point, just this Thomson coefficient becomes 0. So there is no change in temperature with respect to change in pressure. So if I'm decreasing the pressure of a gas, let's say the simple example whatever we consider, from 10 bar to 1 bar, at that particular point my temperature change will always be 0, because I'm expanding it at inversion temperature. Now if I'm expanding it at higher temperature, when I'm decreasing the pressure, my temperature increases. Okay, in other way around, when I'm below the inversion temperature, when I'm expanding from high pressure to low pressure, there will always be a drop. So this can be more better explained in a TH plot. Okay, let me see if I can plot a TH plot. Okay, I'll open the plot. This is a rough prop. Okay, this is a simple tool. Let me plot TH. Step size of 3. Okay, fine. See, these are called constant pressure lines. Okay, now on the y-axis we have temperature, on the x-axis we have enthalpy. Okay, uh, when we are expanding through a throttle valve, it happens at constant enthalpy. Okay, constant enthalpy expansion, isoenthalpic expansion basically. So this is 6.5 megapascal and 3.5 megapascal, which is essentially 65 bar and 35 bar. Okay, now if I'm at this state point, if I'm decreasing the pressure, you can see that we are expanding through a throttle which is at constant enthalpy, right? So my constant enthalpy expansion, isoenthalpic expansion, causes in drop of temperature, right? Whereas if I'm above inversion temperature, it happens the other way around. Okay, so basically these constant pressure lines will cross each other at some point. The crossing point is called as inversion temperature. Okay, so that's what inversion temperature means. Yes, expansion through valve is related to Joule-Thomson coefficient, correct? See, the schedule for this interaction sessions is fixed long back. Okay, I don't think it can be changed right now. Probably during next course only it can be changed. Can we give exam multiple times for certificate? I don't know. This is out of my jurisdiction to answer this. Why are we using water free method? A free water method. See, uh, if someone says that you can get pure water, then he is actually trying to make you fool. You can never get pure water. Okay, it's not possible. In practical, we say that pH of water is 7, right? How many of you have actually tried to measure pH of water? Although you get a distilled water, the pH would never remains neutral. Okay, because getting pure water is just not possible. However, in simulation point of view, we say water is just H2O and there is no ion, solvent, nothing in water. Okay, so to simplify the analysis, we use free water method. Okay, that's the reason. Any other questions? Yes, the classes will be held every Tuesday 6 to 7. Yes, these things, you are asking about this PPTs or the ones which professor is discussing. These PPTs are being uploaded, when you go to NPTEL site, you will be able to see these. Okay. Or do you want me to show where will you get these PPTs in NPTEL website? I can show them. Just comment if you want me to show. Okay. Yes, towards the end of this course, your Aspen license will get expired. This Aspen license is given only for couple of months. Assignment 2 questions 6 to 10 have already answered this PPT, right? This PPT is shared in NPTEL website. You will get this. Yes, data is missing. I've answered this question multiple times, but anyways, data is missing. As of now, please submit only 1 to 5. If I have already asked the coordinator regarding this, okay, if I get a response till tomorrow, I would respond to all of you. In that case, the deadline for submissions will be extended. All right. Yes, your Aspen software will get expired. If you have crack version, that's I would say better not to have a crack. Okay, see, when you go to Swayam website, just go Aspen. Go to this course. Go here. You will be able to see some tab known as problem solving session. Okay. When you go here, it says click here to view lectures. So if you go here, you will be able to see link of the YouTube video which I have uploaded last week. Okay, and the presentation folder is available over here. Okay, so this folder will contain all the PDFs which I am showing you, and the links for each week will be shared over here. All right. So I'm the one who is maintaining this Excel sheet. So if you have any problem with accessing these things, you can text me. Okay. I have personally checked these links; they were working fine. But in case if you don't have, if you are unable to access them, just let me know. While opening Aspen, it says your license will expire on T9. Yes, it will be extended till end of the course. Okay. Can we get professor's PPT? I'll have to check. I don't, because I myself don't have access to those PPTs, but I'll have to check. I'll respond to this question in the next week. Okay. Any other questions? Any other questions?
Sir, in case of
Yes, ma'am. Please continue.
hello,
Yes, you're audible.
in case of separation by decanter,
Yes,
sir, you mentioned about it happens because of minimization of Gibbs free energy.
correct.
So can we instead
Yes.
say
Uh,
that
yeah, please.
in case of thermodynamic equilibrium, we Gibbs free energy, we change in Gibbs free energy is zero, but it is not zero, it's tending towards zero, is it?
Yes.
Oh, okay.
See, no, apparently we say it's based on density, but thermodynamically, if you go in detail, liquid-liquid split happens because of minimization of Gibbs free energy and not because of density. Density is a consequence. Cause is Gibbs free energy. Okay. Yeah, this session is being recorded. Okay, see the same Excel sheet. You have a link. This is last week lecture. Okay. So for this week lecture, I'll be filling this column, this row, column, or whatever. Just block. You'll get everything. All these are recorded. Okay. Anything else? or else we'll stop over here because I have to go for another class. Any other questions? Okay, then shall we end the lecture? Okay, seems no responses. Okay, fine, then we'll see you next week in that case. And do come back with the question which I have asked, okay? Difference between Underwood and basically the approximate model and the rigorous model. What is the basic difference between these two? Okay, then we'll meet next week at the same time, Tuesday 6 to 7. Okay, then.